Okay, hello everyone. I'm very happy to be invited today for presenting this talk related to the implementation on Cortex-Lab of NB-IoT framework under GNU Radio. This work has been done in the Maracas team, so my presentation is on behalf of the team with strong involvement of Leonardo Cardoso, especially on the GNU Radio implementation, as you will have a course today and tomorrow about the use of Cortex-Lab on GNU Radio, with Otman Ubeja, who was an engineer in the group, Mathieu Imbert, another engineer, and Diane Duchemin, a former PhD student, or Yasser Fadlala, a collaborator from Lebanon. So I will try to synthesize all this work with a few slides. Okay, so first let me describe the problem we want to study with a Cortex-Lab and GNU Radio implementation, and then I will go for the proposed solution and a few results. So what we are concerned with is related to Internet of Things. So currently many objects, many things are going to be connected to the Internet to simplify, to promote the interaction between the virtual world and the real world. We may have cars who are looking for vacant places. We may have tools which may be connected to find them, to optimize their battery, their behavior. We may have sensors to measure the environment, to measure the temperature inside building or underground. And we may get all this information to provide as an output some recommendation, even some actions on some equipments. So, for instance, to control the temperature. So we have different properties in this IoT configuration. So in the IoT configuration, we have very specific communications features. So the main features compared to classical wireless communications are following. First, we have a massive access. Okay, so it means that we may have a potential of many nodes which may behave in a random access. This is one important feature which is not so common in the classical wireless network, with some rare events. So some sensors transmit only for a few milliseconds and then switch off for a couple of hours. And to evaluate a technology, a phi layer or MAC layer technology, we need to work with many nodes. We cannot just try one transmitter and say, okay, we are done and that this protocol is working well. We also consider that most packets are control packets. What does it mean, control packets? Control packets means that they are, for instance, for robots, for cars, etc. Okay, and so they are made of small information quantities. So we don't transmit data flow with a high rate. We transmit small information. We want reliability. In some cases, it's a very important criteria, and we have to fulfill some latency constraints. Sometimes we may refer to this context as URLLC for ultra reliable and low latency communication. This is one of the main features for 5G communications. And we have also to face long-term variations. So if you deploy a IoT network, you may increase the number of nodes or their activity may change over time. And so we are interested by learning protocols. So we would like to design protocols which are able to learn their optimal behaviors. We may adapt to density variations. We may have also correlated data which may impose to change some properties of the system. So we have to deal with many features of merit. We want to ensure reliability, responsiveness, massive connectivity. All the things are related to the performance of the transmission. We also have limited resources, which are mostly energy and spectral efficiency. We may have software and hardware limits, and we also have to comply with security and privacy issues. So this problem is a very high complexity problem that we have to deal with. In addition, we have a lot of technologies which are promoted to be used for IoT. We have Sigfox technology based on the ultra narrowband. We have LoRa technology based on chirp and wideband. We have other technology like LTE, GSM, 5G, etc. And we may have like vision of time frequency structure, for instance, for OFDM or even for Sigfox access, where we use very narrow transmissions in the frequency band with random access, and we have such kind of peaks of activities, and the receiver has to decode as much packet as he can. Okay, so the objective of good technology is a technology which is able to transmit these packets, fulfilling the rules that I mentioned before, so ensuring all these constraints or finding a good trade-off between all these features, which is not so easy. So usually when we work on this kind of problem, we may have different works, and this work has been supported by the National Agency for Research with three projects. One was basically based on a theory, so by math, we try to represent the performance of different systems and try to find new solutions from a pure theoretical perspective. We may try to design some protocols, evaluate them by simulations, as we did in the eField project. And in this case, we have a guarantee of performance of a given system, but we are not sure if it's the best one. And because simulation is not sufficient, we may also do experimentation. But experimentation is very costly, because if you want to deploy 500 nodes on the real domain, you have to ensure that you have the right to transmit in this radio frequency, and so on. So experimentation is nevertheless very important to give a feedback for simulation and protocol design, and to update the models and assumptions for theory. So what I will present today is something that is not pure experimentation, is between experimentation and simulation. Using CorteXlab, the idea is to be as near as possible to a real environment, but at the same time to have a fast and easy system to evaluate the performance of new technologies. Okay, so let me switch for the next one. So what we want basically is a given structure as represented here. So we may have one base station. So the system is very asymmetric. We have one base station. We will, as in a real system, we may have more base stations, but in this system I will consider one base station. We have sensors which are deployed over the area, which are under the range of the base stations. And the base stations may send a beacon or a synchronization system or a request broadcasted over all the channel. And then each node may transmit information. But because we don't know which node will transmit information, we cannot use a classical scheduling system centralized by the base station, because the base station doesn't know exactly which node wants to transmit some packet. So we have a distributed systems, and our objective is to evaluate the physical layer, the MAC layer, and the scheduling system associated with this problem. Okay, we also want to have a connection. So what we would like to have is a link from the user, yourself for instance. So there is a user that would be able to program and to connect to all the nodes and the base station, to program this node and to evaluate the performance of this system. So what we want to build and to evaluate is a system that is under control. So it's not a perfect real system, but what we want to have as a real system is the red uplink transmission represented here. Okay, this is what we would like to evaluate. So our system is expected to be a fast and semi-experimental assessment of a complex system. We want to be able to fast test and try environments, so the remote access. We want a reproducible environment, so an interference-free environment where we are sure that if we run an experiment, nobody will perturb what we are running. And we want a system that is adaptable to almost any physical or math layer that may be proposed currently with system or protocols and also on standards and also in the future. So this is why our system is based on the software radio equipment. So before going in the detailed implementation, let me give a few words about Fit CorteXlab. Even if in this conference you will be learn much more about it, I will introduce very quickly and very briefly what we want to do. So CorteXlab is a cognitive radio test bed and experimentation lab, which is a facility for state-of-the-art physical layer, but not restricted to physical layer. You can run also tests on Mac layer and scheduling and machine learning for resource allocation, as I will illustrate in a few minutes. This CorteXlab is remotely accessible to the global community of rare earth experts. You can use it. Any of you can request an account and use it for your own research and to collaborate on some project. The idea is to create an open source community when you can compete your code to other code produced by others and evaluate your code on some already defined scenario, which is quite an important contribution in the community. So what we have mostly Pico SDR and URSAPs. So the most nodes we use today as the URSAPs, the National Instrument URSAPs, which may be SISOs, so single antenna, and the Pico SDR are MIMO antennas. And we are currently deploying other URSAPs which are MIMO and which increase the available bandwidth for processing up to 160 MHz and over the frequency band from 6 MHz to 6 GHz. So you already have two of them which are deployed in the room. And we expect to replace a couple of the SDR SISO nodes in the future by these technologies. So the nodes are in a room. The room is shielded, so we have no interference. We can work in our private area. You can connect to each node, so you can deploy code in any node. You can control the code in any node, and you can get information from these nodes. Okay, so that's a very important feature of CorteXlab. So to give you a better illustration, this is the room, which is shielded, partly anechoided, so it's not a full anechoid room because we want to have few fading and few realistic channel, but it's partly anechoid to avoid having a reverberation room. So, and then we have a grid, so when you program, if you program node 28 or 16 or 5, you know exactly where it is and how far it is from the other nodes, so you can select the topology you want to use for your experimentation. Okay, and as I said before, you can just connect to the server and then program the nodes. I will not go in detail on this topic because you have a course today or tomorrow on the use of this environment. So the idea is really to provide a multi-node tool to run your own experimentation. And what I want to show today is an example of the kind of things that you can do with such experimentation. So the objective is to propose a framework for IoT massive access on CorteXlab. Okay, so if we look at the architecture I proposed before, which is this the architecture also drafted on my screen, what is a node? So for us, a node will be one physical layer, which may be flexible. So we want to be able to change this physical layer. We may have a MAC protocol, which is the methodology to access the medium. You may program an Aloha technology or CSMA or whatever you want, an algorithm to access the medium to select the radio resource. And then you may have also link layer management, so you may define the strategy to retransmit a packet when the transmission failed, or to program HRQ or anything you want. So basically, we are mostly interested by these three transmission blocks, and we have a resource radio management block which will control the transmission of these three steps. And what we have on the top of that is a data source, so we want to be able to mimic any source of data from the sensor side, which will be sent in the infrastructure. So the idea is really to map on CorteXlab. So if you see this architecture, we may want to map some nodes as sensor nodes, one node as a base station, and to run a real experimentation of uplink access for IoT. Okay, so now what we did, we defined two kinds of nodes, one BS node and one master MS node, which is a master sensor node. I will explain why master sensor, which is implemented in a node. So what we call a node in CorteXlab is the association of one computer and one USP, which provide a node. So one node will be elected as a base station and has a specific program, and other nodes, as many as you want. We have up to 20 or 40 if you use all the nodes, which may host master sensor nodes. So why do we have not directly a sensor node? Because we are limited by the number of USBs and PC we have in the room. So the idea is to host several virtual sensors in one GNU Radio computer, and so each of them is programmed as an independent sensor. So if your computing capabilities in the nodes permitted, you can program many nodes as you want, and they will run independently. But what is important is we will have a synchronization, which will help to get the synchronization information for all sensors. This one is mutualized between all the sensors to save time, and all the nodes will get feedback information from the base station through the Ethernet downlink. So the idea on this work is to focus on the uplink. Draw here in red, okay, and then so what we have here, and the feedback that the base station may want to send to the nodes will be sent in our experimentation by the wire link. So it means that we have an error-free feedback transmission, which was important for that. So what the base station node does, it programs a beacon generator and it creates a frame structure to have a multi-slotted infrastructure that the MS nodes will get at the synchronization node. Okay, so the BS node will send packets, which is to generate the beacon, and this will be emitted, which allow to synchronize all the GNU Radio based computers hosting the nodes. So then we define a scheduler. So the scheduler governed by the base station provide as a transmitter. So first the base station is a transmitter, transmit a broadcast channel like a beacon to get the initial synchronization. So the initial synchronization is get by all the sensors, and we define a structure which is shared initially by all the nodes with slots. And so you can program the selection of the slot you want to transmit in. So for instance, one sensor may try to transmit always on sensor 0. Another sensor may decide to alternate the transmission between slot 0 and slot 5 and so on. And the base station will try to get information from these transmissions. And once when the base station has got all the information, it will store all the information, and from the wire link, the sensor may evaluate if their transmission has been a success. What you see in red and blue here as a silence period, because sometimes we need to do computations which take time. So to avoid a real-time problem, we may add in our system some silencing period during which the different elements may do some pre-computation to guarantee that when we transmit in the slot, we are all transmitting at the same time in this slot. So this is like a flexible things which allow to run complex computations. Even if you have complex computations which cannot be done in real time, you can increase a bit this period, and then you ensure that your scheduling is working properly. So that's basically what we have programmed. So if we look inside a CorteXlab node with multiple sensors, so we have multiple sensors. All these sensors generate IQ signals. All these IQ signals are summed before being sent to the UHD interface and and to the room, into the wireless. Note that the IQ signals are built independently and summed after a digital channel emulator to add channel diversity. So we may detail very quickly the different blocks. So the USRP device provides the interface between the radio frequency and the digital domain, the baseband signal. Then the UHD provides the discrete signal, provide the input to the synchronization to receive the beacon and to provide the synchronization time to each sensors. Then we have the Ethernet downlink, which is used to get feedback from the former transmissions. The UHD is the classical GNU radio block, which is used to control the USRP, the parameters, and it is the digital analog interface. The synchronization, as I said before, detect the beacon and provide the time slots for the nodes. And we have data bits, which is the payload emulation. So you can program here any data source you want if you have temperature sensors, if you want to put a fixed data input and so on. So you can modify this block. At time, we have a random data, just put an input. We also, of course, have a physical layer. So the basic physical layer implemented is inspired by NB-IoT. So we have different blocks. I will not detail all these blocks, but we have a convolutional encoder, modulation, FFT, submapping, IFFT, which are the classical blocks that you can find in a no FDM-based transmission. We can replace this physical layer by any other one. In the results, I will show some results with also a homemade turbo FSK transmitter. And we have an access policy block which allows to program the rules for transmitting. If you want to change any parameter of any slot, for instance, if you want to change the slot you are transmitting and so on, you can program here the access policy. So this is basically the general scenario. And then the local scheduler get the information like the access policy, form the slot structure and transmit the data at the right time. We then have a channel emulator which allows to introduce some fading pass loss to decorrelate the channel between the different sensors hosted in the same node. And then we zoom all the all the IQ signals to be transmitted through the UHD to the RF output. Okay, so I don't have time to give too much details on that, but we have in fact a state machine behind this, which means that the transmitter is idle. We generate the packet in advance. When it's ready for transmitting this packet, so during the red silence period, he goes to the listen period. So he's listening, waiting for the beacon. Once the beacon is detected, so we move to the BCH state, and then we are ready to transmit the appropriate packet in the slots according to our scheduler. We have also to fulfill the word interval, so we transmit in each slot if we have something to transmit. Then we proceed at the receiver at the base station, and then we come back to be ready to prepare the next slots from the data and access control. So this programmation is really a mixture of state machine and data flow, and this was an important aspect of this kind of work. So why did we do sensor simulation? To increase the number of nodes that we can generate and simulate in our system. Why tunable waiting periods? To absorb computational overload. And as I said before, we have a mixture of data flow programming and state machine. So we did some experimentation with that. So for instance, we compared the physical layer NB-IoT with a turbo FSK based physical layer. And after the run, we may observe the detection rate. So for instance, here we have a purely random access. So we have 10 nodes, 9 nodes are transmitting as interferers always on the same slot, and we have one node which we are looking for its performance, which is transmitting on a random slot. And since this node transmits on a random slot, it can at the best have 10% of success, so it's about 90% of errors. But when we work with the turbo FSK physical layer, which include a specific coding allowing superposition, we show that using this kind of physical layer allows to reduce the error probability. We also measure the detection rate, what is the probability that the packet you want to transmit has been detected, and at the multiple access layer we have again different nodes which transmit with some probability, and they have a policy, which means that if they succeed to transmit in some slot, they will continue to transmit to this slot with a high probability, and if there is a failure, they will change with high probability to try to find another resource. And we see that after some time we have some stability, and it means that the nodes have selected their resource and are able to transmit. The UCB technology, MAB, means multi-arm bandit, which is like randomly selecting among the different frequencies. And UCB is a method where you trade between the exploration, so looking for new frequencies, and the performance evaluation. But I will not go in detail on the performance of this kind of algorithm. So the takeaway messages are the following. With CorteXlab, you can design a multi-user system with many nodes. In each node, you can program different sensors, and you can very, very quickly reproduce this programmation by putting this code over all the nodes, and then you can run the experimentation and get very interesting information, which is a mixture of physical layer, MAC layer, and scheduling constraints or solutions. Well, thank you for listening to me, and I will be happy to answer your question now. Thank you.